I'm going to make tonight's presentation in two pieces, largely because the first one will be a bit of a background about the smooth particle hydrodynamics technique and the development that we went through to enable this Australian Research Council project with the defence guys to, just to start. And then the second half of the presentation will be a presentation that I made to the Pacific 2019 conference last year. And because of the content and the people involved, that's got to go through a certain process before we can have that as a public presentation. So that'll be the second part of the presentation, and that'll be more about the work that we're doing at the moment with the defence guys and the other universities. So I'll start on this presentation here. So there's a bit about me, and I think most of you would have seen that already in the blurb about this particular show. All right, I just need to be aware that it takes about a second or two between when I hit the button here and when it updates on your screen. So that's me. I'm employed under this project as a research associate at the University of Newcastle, but I also work as a senior engineer at Pacific ESI in Sydney. So the software we're going to be using is this VPS, Virtual Performance Systems, and we're talking some more about that in a minute. This looks an awful lot like the ARC presentation. Anyways, this is the main project itself is this ARC linkage grant, and we've given it the title of the Structural Integrity of Maritime Platforms. And the reason we've chosen that title is nice and broad, because these techniques don't only apply to floating structures such as ships, but other things such as perhaps platforms and FPSOs and anything basically out there bobbing around on the ocean. So in the ARC project, we've got these four companies: Defence Science Technology Group, Pacific ESI, and the two universities with Professor Rob Melchers and Professor Chong Min Song there. So the aim of this project is to develop a tool that gives asset owners a more confident method to predict the likelihood of a given asset surviving a given service load. So what we mean by that is to take out some of the probability that's used in a lot of the classification society means of assessment of loads on a boat or a structure. So one of the applications for this might be to do the analysis that'll give us a better insight into the life extension of existing assets or survivability of an aged asset. Subject to a specific load is the key here. So this was at the outset of the project, this was the real aim, just to reveal nonlinear stress response of a ship as it traverses a wave, to really get a much better understanding from an engineering perspective as to how the structure, particularly an aged or damaged structure, might be responding to large waves, basically, or a limit state incident. Or really a vessel that is not able to be analysed by conventional tools. So it might not be a conventional ship shape, and it might not conform to the usual rules of thumb that we have or the empirical formula. So again, whatever you want to use the results for: risk assessment, survivability assessment, life predictions, fatigue assessment. And the real key here is that we're looking at non-linear responses. And I guess that's this last comment here. The technique can be used for linear responses, but it's not efficient compared to other tools which naval architects are familiar for this purpose. So we might be able to reproduce an RAO of a boat, but it'll take us an awful lot more CPU time and effort than to push the button on your Maestro or other software. So the software we're using here is a general purpose explicit FEA software. It's produced by the French company Engineering Systems International, and the largest user base for this particular software is the automotive industry. And the user interface kind of reflects this. It's got a lot of tools for metals. It's got a lot of predefined post-processing tools for looking at limit state diagrams after you've stamped a part or crashed a part and things like this. It also has a lot of other features that, which is kind of novel, and we're beginning to see how these could be used in the naval field as well, particularly crash test dummies. So you'll see an example of that later on. It's a general purpose solver. It's an explicit and an implicit solver. And it also has, I didn't make mention there, but it has inbuilt mesh-free solvers, such as the smooth particle hydrodynamics and the finite point method. And there's a vast library of existing models for materials in there. And the most important thing, what we're interested in here, is they're non-linear models. So we can model the failure of things as well. And that's in crash analysis of cars, that's really what we're all about. It's about predicting failure and the progress of the failure such that you absorb as much energy as possible before the occupants get in harm's way. So here's a snapshot and a bit of a teaser as to what this project is all about. So this is a generic frigate going along in 4-meter waves at a speed of 9 knots. You can see the fluid behavior there. There's all sorts of things, a bit of splash at the bow, and there's some turbulence near the transom. We'll have a look at these in closer detail later on in the presentation. But that's in a nutshell what we're trying to do here. We want to model a full-size model of a boat as it goes through the waves. And the interaction of these two is purely driven by the physics defined in this general purpose FEA software. But that's a long way down the track. How did we get there? First of all, how does this work? What is this smooth particle hydrodynamics? How do you set up a model and what actually happens? So as we mentioned, this is like physics modeling software for virtual prototyping of things. Things can be anything. In this particular case, it's a really simple example just to show the fundamentals. The red box is like a cross-section through a boat. The blue pile of little stars is our little particles representing water. And then we've got this black thing down the bottom, which is the tank. So in the software model, we define the properties of these things. The boat, it might be steel, it might be fiberglass, it'll have some sort of stiffness and some sort of limit to that stiffness. And then the water, it'll have properties associated with some fluid, ideally water if we're talking about boats. And then there's a tank there that's kind of rigid and defined and held in place. So it doesn't really matter what it is, but it's important that it contains all the water and it prevents things from falling out. So when we set up the simulation, we describe how they interact. The water can't go through the side of the boat. The water has to stay inside the tank, and there's gravity acting on everything. And basically, once you've defined that, you just let the simulation go, and it'll come to its own equilibrium if you've got things set up right. So in this particular case, you can see at the final state of that simulation, some water actually ended up inside the boat, and that kind of fell to one side, so the boat has a bit of a list. Meanwhile, the water on the outside has come to a new equilibrium point from where it started, and that defines our water line for our boat. So pretty simple, but there's a lot of fundamental things going on here, and I did a lot of these simple simulations just to understand if this software is going to work for this application, and then what you need to do to kind of control it. So just briefly, the smooth, where does the smooth come from in the smooth particle hydrodynamics? The smooth refers to the smoothing kernel, as we call it. That's this function that is strong in the location of that center particle that we're looking at. This diagram on the right, all those little circles represent our particles that are representing our fluid. And the big circle around the outside is what we call the sphere of influence. And then that weighted function, that little kind of Gaussian curve or whatever it is how that particle in the middle interacts with the particle next to it and vice versa. So out at the edges of the sphere of influence, there's almost no interaction at all. Beyond that, none of the particles there would know about the particle I. So this is how it works for all the properties of that particular particle. Its parameters, its properties are defined by the smooth average of all of its neighbors. So that includes its velocity and its density and these sort of things. So we're now using it for quasi-incompressible liquids, but its history of SPH came from astrophysics, and a very prominent guy even from Melbourne was one of the kind of founders, if you like, of this principle of the smooth particle hydrodynamics. But I'm no mathematician, so I'm not going to go into this for too much more. I'm much more interested in using the software. And some of the early applications, this is back in 2003, was the ditching of commercial aircraft. So we have a flexible, a structural model of an aircraft, and it's going to land in this ditch, this little channel of smooth particle hydrodynamics, and then the SPH contained within these bricks of finite elements, just to kind of save on CPU time. I just lost my mouse here for a moment, so I can't get this video to go. There it is. So the velocity, the contours, the colors of those particles is represented by the color. But you can see the plane impacts. We can measure forces and things on these things. This is quite early work. Much later on, they're looking at deformable models, much higher resolution of the water and these sort of things. And these days, this is actually an acceptable a process for modeling the ditching performance of your aircraft and for the bird strike on aircraft. So bird strikes are a big thing for aircraft, and we can model the bird strike. These are not the frozen birds, these are real live flying birds as they impact the aircraft. And critically for an aircraft, it's the control surfaces which extend out of the front and back of the main wings, which are prone to damage from birds. And of course, when an aircraft takes off and lands, it's close to the earth, that's when it's most likely to run into birds. And it's most likely when you need the performance of these structures. So we model the bird by this blob of these SPH. And this is how some other guys did the testing for this to calibrate the bird. There's some very well accepted results for bird splats, and there's pressure profiles at various locations on this target plate. So we're able to adjust the SPH parameters of the blob to reproduce what the real bird was doing, and then we can apply that real bird to our structure in the finite element package. So in Australia, one of the earliest projects that used the SPH that we're aware of was through the company Pacific ESI and Hawker de Havilland at the time, who had the contract for design and build of all the control surfaces on the 787 Dreamliner. So typically for this process, the bird strike certification, you actually have to produce these parts, all 31 of them or however many there are, and then conduct a physical bird strike test and then measure the results. Through this work, we were able to validate and verify that the smooth particle hydrodynamics within the VPS software can model this process quite well. It's also essential that we have the modeling of the composite materials at which they're being fired against calibrated as well. So these structures here are fully composite carbon epoxy structures with internal structures as well. And this whole process modeled the impact of the bird against the wing and the failure of the composites. And through one full-size scale test article like this, as we see here on the left, on the right, sorry, they were able to satisfy the FAA in the United States that the numerical process was adequate for modeling bird strike. And the Boeing 787 was the first commercial aircraft in the world to use numerical simulation of bird strike for certification. So these are some of the results. We had a bit of a challenge. We had to predict how much bird velocity would just create damage and then measure that, and then how much would absolutely obliterate the skins and the structure. We can't show you those pictures of those, the Hawker de Havilland parts, the Boeing parts, but we have these sort of things prepared for training for other people who want to use the software. So this is a typical, generic wing being hit by a generic bird, if you like. And the critical things here are the way that the bird breaks up and splats and goes in all sorts of different directions, but some of the bird ends up inside the wing. We get this very nonlinear behavior of the materials, whether it be aluminium or carbon honeycomb or whatever it is, or metal rivets and all sorts of things in these sort of simulations. So that's the kind of thing the general purpose VPS software is used for. I'm interested in things that float, so namely boats, but also helicopters often hit the water and not always with the consequences that you want. So that's typically what happens to a helicopter when it ditches in the water if it doesn't have any of these emergency flotation devices. That's not surprising. The engine's at the top of these things, so they're very top heavy, and typically as soon as they hit the water, they roll over and sink very rapidly. So allowing the aircraft to stay on the water for as long as possible greatly enhances the chance of egress of your occupants. So here we have an interesting application where there's a helicopter again, but we've introduced some of these airbags. So these airbags are the same materials that they use. Sorry, I'll go back a bit. As remember, this is automotive software, and airbags are an essential part of the safety of any modern car. So our software has this ability to model these airbags. So you can see that they're on the side of the helicopter. They start all folded up, and as soon as they impact the water, they inflate. And then, lo and behold, if you get things right, the helicopter stays upright. So we're able to model this process, and we've had a few little jobs like that along the way. I just did some other simulations illustrating the helicopter falling at different angles as well. I hope these videos are coming out all right. They're perfectly smooth on my computer. Okay, so all this stuff is really about fluid structure interaction. So another nice simple job that we sometimes run when we're training is dropping of a soda can onto a hard edge. So this is, just an aluminium soda can hitting a right angle bend. And once again, all the SPH, the fluid inside is modeled by SPH. That's these little white dots. And as the simulation progresses, the can starts with a downward vertical velocity, hits this thing. You can see that the can bends, and there's a lot of slosh and things happening inside. So that's the principles. It really is quite simple to model once the physics is set up correctly. And this has been used for sloshing of fuel tanks in cars, obviously, but as well as tankers and things like this, just to understand what goes on. Here's another interesting little problem where we have, it's not really a problem, but a demonstration of the FSI, water inside a bottle. So this is a quarter model of a vertical bottle, if you like. It's got a kind of soft, flexible bottom down the end. And the one on the left, the water's just sitting in the bottom. The one on the right, the bottle has been pre-spun, and the water, the same volume of water, is all just clinging against the sides. And then as the bottle is dropped, there's this kind of energy dissipation through the fluid structure interaction inside the bottle. So this is an interesting little problem that colleagues in Chile are working on. They're interested in interesting fluid behaviors and fluid structure interaction and wave creation and things. So this is just an interesting little demonstration of fluid structure interaction. Of course, I'm interested in boats, so it didn't take long before I put some sort of boat in the water and demonstrated that it could move, and with any luck might even interact with a wave. So this is a generic VO70 kind of boat, Volvo 70 boat from a few years ago. The boat has a canting keel, but there's no aerodynamic forces generated. I just put a mast on it and put a force representing where the thrust of the sails might be. And then the response of the boat is purely as a reaction of the canting keel, the thrust from the sails, and the interaction of the water. So you can see it bobbing over the waves, and yeah, bow comes out. It's kind of interesting. It doesn't always work. I often forget to kind of set something up quite, and it's like, oh, damn. But what's interesting is that even when you get things wrong, the software will still proceed with the physics that you describe and the conditions that you describe. So you can see this might be what happened if your, I don't know, keel fell off and you ended up on the beach. Anyway, I digress. Some other little simple little applications are just a chined monohull with speed. The curve down the bottom right hand shows pitch and heave as the velocity of the boat increases. So it gets to a certain point where it's up on the plane, and then things stay relatively constant, pitching a little bit, but the heave remains the same. I haven't validated any of these results. It was purely looking to see if the resulting behavior of the boat would be as you would expect. But until, of course, it runs out of water and it falls off the edge of the world. So other things, I mean, you can basically model whatever you like in this software. We had a brief inquiry about this sort of thing, so I just demonstrated A simple simulation of a lifeboat falling into the water, and obviously there's more to it than meets the eye. Too much buoyancy, wrong angle, whatever it is. But what's interesting is it's modeled what we defined for the parameters for the model. And then while we're doing all this stuff with displacement, with boats and ships, we had to verify the displacement is correct. So this is a little 2D job where the square here is introduced into the water under a controlled displacement condition. And what I'm interested in is what the buoyancy force on this particular box is as it is pushed into the water. So I kind of defined relatively fine particles for this, and well, it was really quite interesting just to observe the fluid behavior as well. The vortices coming off those edges, the splash at the start of it, and the free surface, the complex development of some waves and all sorts of things on the top there. That wasn't really what I was interested in. I was really looking at the net force, the buoyancy force, to make sure that all that was as it should be. But just to watch the fluid dynamics was pretty exciting as well. So it looks like it inherently does the right thing. Again, another demonstration purely without any validation or verification was this submarine without any controls on it at all. No thrust, no velocity. No, it's not being fixed. It's just wallowing around there as though it's lost motive power or whatever. And as the waves go past, you can see it has this corkscrew motion. So for this particular simulation, we've modeled the depth down to the grid, and then the grid is a moving floor. I'll talk about that a little bit more, which creates the waves. And then I've just removed everything but the top surface, so we can see what the waves are doing and we can see what the submarine is doing underneath. So the boat has, the submarine again has, oh, that is a boat, that's right. Actually has 6 degrees of freedom, and it's just interacting due to the fluid forces acting on it. Something else we've been doing at Pacific ESI was we had a little project looking at blast protection of vehicles. A key part of that work was calibrating the explosive. So, well, that's fine. That was a job. It was really interesting. Got some good results out of that. But what I was really interested in was boats. So we put the explosive underwater, monitored the pressure pulse, and we parked a boat next to it, which was defined with some elastic plastic hull structure to see if we could actually model the damage that would happen on the side of a boat. So this is just a view of oh, thank you, just got a comment from somebody saying the videos are working well, appreciate that. So in this, where I've just stopped the video here, we're seeing some of the plastic deformation that has occurred on the side of the boat. So this is just modeling how that pressure pulse is influencing damage on the side of the boat. And the only thing we've defined here is the contact interface interaction between the ship and the water. The contact interface is the magic rules which just keep one thing away from the other. So you can see that the plastic deformation, it actually happens incredibly fast. This whole simulation took place in about 10 milliseconds. So it's hugely slowed down in this animation. But what I was really interested in to do was then to model the flooding that might happen. So this next picture is just a still picture of the resulting damage from that underwater explosion. You can see it's perforated the hull in a few places and blown some stringers off the side of the boat and things like that. So to use this in a flooding example, I repaired the damage, if you like, just by putting an intact hull plate over the outside of it, and then I can remove that in an instant numerically, and that would then leave this perforated hull structure with the holes already in it, and then the water could just flow in through that hole, so I don't have to model the explosion every time. So this simulation here, I've just taken the top of the boat off, well, this is the ship, and we can just see down to the deck levels where the perforation on the side is, and we're going to drop this particular simulation will drop the boat into the water with the hull intact, let it acquire its hydrostatic equilibrium, and then we'll instantaneously remove that patch over the side so that it's got that hole exposed. And then we'll be able to see how the fluid comes into the hull through those damaged areas. So you can see it quickly fills up one or two compartments there. There were some other holes in this particular model that enabled the water to flow underneath the floor and longitudinally along the boat as well. Okay, so in contrast to that explosion animation, the time in the right-hand corner here, this is in seconds. So you can see this is actually speeded up quite a lot, sped up. But that's just another application here. We're just modeling the fluid and the structure interaction with some very simple rules as to how they interact. So here's just 4 snapshots throughout that simulation. The top left, the boat starts out of the water to make sure there's no fluid inside the water, no water inside the boat, sorry. The tank is a kind of unusual shape, but it's just big enough to keep the minimum number of fluid particles and then allows the boat to float. In that second step there, it has its hydrostatic equilibrium. Then we remove the patch off the side, the water comes in, you can see the boat acquires a list. And then because it's a numerical thing, you can get numerical output. So here's a graph of something against something else. So we have both the heave and the roll with time. And so this first big dip here is as we drop the boat into the water and it acquires its hydrostatic equilibrium. This point here at about 10 seconds is where we remove the patch off the side. Water flows in, so it obviously rolls to one side, and then it progresses to sink a little bit further until things achieve a new equilibrium. So that's an example of UNDEX and flooding. So as I mentioned earlier, it doesn't have to be a boat-shaped thing that we drop in the water. So this was just looking at the stability of this hyperbaric rescue chamber. This was a rescue chamber that they would jettison from the side of a boat or from the side of a ship if they needed to evacuate the ship in a hurry. So they were a little bit concerned about what would happen to this thing once it hit the water. And one of the requirements was that at least it would stay upright for the occupants inside. So in this case, I specifically placed it in the water upside down and let the simulation run to demonstrate that it would right itself. So the nice thing about this is it's not a boat shape, but it still works. Oh, look, this isn't a boat shape either. But I just had to do this because I could. This is what my computers were doing over Christmas while everyone else was on holiday. Sorry, I'm going to run that one again because I really like it. But look, it's the same principle applied to all these jobs. That is, the water is represented by all these little particles, and you've got some structure, and they interact by keeping out of each other and having some sort of drag or friction against them if they do. You can see here we've got some contours of some wake or something like that, bit of splash happening there. It really doesn't matter what the object is that you throw in the water. If it's going to float, it'll float. If it doesn't, it'll sink. This contour here is showing the velocity of the particles. So here you can see when the particles, there's a lot of splash involved, and when that splash kind of lands back down in the water, we get these exciting little pink bits just suddenly kind of splash against the water, and you see the local area of high velocity. Okay, yes, we've seen that one. So here's another kind of unconventional boat. It's a catamaran. I did this one quite a few years ago. So we've got this thing going in waves, and I've just got a thrust vector on the transom to represent the water jets that a vessel like this might have. And what's interesting is to see the corkscrew motion of the boat that results. So its fore and aft speed changes as it kind of goes up the back of a wave and then down the front of another wave, but also this corkscrew motion. I don't know if you guys have been on boats like this, you'll know that's exactly what happens. I'm a sailor, I've got a catamaran as well, and this motion can be rather uncomfortable. But it's realistic, and the only thing we've defined here is the physical parameters of the boat, given it a thrust vector on the transom. The nice thing about the thrust vector is that if the boat changes direction, then the thrust changes direction as well. So that's indifferent to a tow tank where you've got a fixed post and it's going to go at a constant speed, irrespective of whether or not the boat is trying to go up a wave and then down the front, down the back. You don't get any of those surge variation in velocity as in the tow tank with a fixed speed carriage, whereas this sort of arrangement it's just got a constant thrust on the back. So if there's a steep wave, it'll slow down. Okay, I mentioned earlier I like to put crash test dummies and take them for a spin in their boat every now and then. So that's what we did. And I got this kind of geometry from a video of a boat jumping off a wave, and this is basically the attitude and angle that it had when it came down to land. So, better. Just go back another one. There's a video missing here somewhere. Hang on a tick. Okay, here we go. So this is one of our crash test dummies from the automotive industry. And you can see it's got articulated joints, and the seats also are sprung to some degree. And this was going to be a comparison between a rigid seat and you know, an impact absorbing seat, just to show the difference in behavior. And being a crash test dummy out of the automotive field, there's sensors all over that model, so you can get the compressive load on the spine. And it will be interesting just to demonstrate how that changes with a impact absorbing seat. So another trial here was generic patrol boat, and I'm interested in the distributional load along the hull. So here it is floating in still water, and we can resolve the vertical load along the length of the boat by these contact interfaces that I mentioned earlier. But then we can also get the boat moving forward and jumping off waves, like some of those great publicity photos. And we can look at the loads occurring on the bottom of the boat during these sort of events as well. So I'm just going to progress through here. There's like 8 instances of the boat progressing over one wave. So the curve at the bottom is some sort of load on the bottom of the boat. And you can see that it kind of matches with what's happening in the top. So the bow's out of the water, there's no load on the boat. At the back, that's going to be a combination of the dynamic load as well as the hydrostatic load. We don't resolve between those two. It's just the net result of the physics of the boat interacting with the water. And here we can see that localized, there's some quite large loads occurring as the boat slams back down into the trough of the wave. Progresses a little bit further. The bow's heavily submerged now. So these are just some snapshots as this boat is traversing over one wave. But in the simulation, this is occurring hundreds of times a second. So we can get these sort of results out as a complete animation, and every one of these locations along the boat has a force that varies with time. But just to represent the you know, the comparison of those loads and those 8 instances, they're just overlaid over the top of each other there. So you can see that in some instances on the boat, they're quite a bit higher than the still water case. Not surprising. It's all kind of encouraging and kind of leads you to believe that this software might actually be doing the right thing. So that's when we approached some of the DST guys and applied for an ARC project to work a little bit further on a particular project. And that's the end of the first presentation. So if you just bear with me for a minute, I'll just swap to the Defence Pacific 2019 project presentation. Right, get out of it. Sorry, it's on this PC behind me, on the other computer. Okay, how are we going, Jesse? Keep on going, do I? All right. Hope you're still with us. So this is the presentation. Thank you. So this is the presentation exactly as I made it Pacific 2019 last year. A couple of logos and things from the various partners. Some of this I've already mentioned, so I'll try not to repeat ourselves too much. That's the 4 people involved. This was originally a 3-year funded project, which was due to finish in this year, 2020, but we made another application and were very fortunate to have won another 3 years of ARC funding. That was announced in May 2020. So that's wonderful news, and we'll be able to take this technique, working with the defence guys and the universities, a lot further than what you see in this presentation. So the main aim, what we're trying to do here is we're looking at a boat that's been in service for a while and might have degraded through its natural use, if you like. So what we mean there is that corrosion or cracks that might have developed through the operation of the boat. And what we want to do is now perform a structural assessment of the boat with those sort of defects in it and see how the degraded boat, if you like, is going to respond to specific incidents of, relatively high load, so limit state conditions, and run this sort of analysis with a known wave and look exactly what's going to happen to the boat. So here's a comparison of different ways you might approach this sort of problem. So in the red box at the top, you'd have a bunch of semi-empirical formulas. You might do some tests and get some uniform static pressure loads under these sort of assumed conditions. Apply your rule-based formula and you'll get some stresses and deflections. That's one way to do things. The blue box down the bottom, you might kind of combine a bit of modeling, model scale experiments to validate some CFD and some strip methods. And then from those, you will get some loads out on the side of the boat and then apply them to your finite element analysis, and then you'll get your stresses and deflections. Or there's this little green box in the middle where we just say it's going to be a fluid structure interaction. We're going to let our ship interact with the waves in a holistic way. All the fluid and the structures are solved simultaneously at every step, and we get stresses and deflections. So that's where we're going. That's what we're trying to do here. Yeah, so far seems to be working. So, as I mentioned here, we're modeling the fluid, we're modeling the structure, and we're going to let the two interact, basically through the rules of physics that are defined in this software program, the VPS, Virtual Performance Systems. It's important to note that it is the one piece of software has both the structural solver and the fluid solver in the one package. And we can determine how often they interact, whether it be every time step or every couple of time steps. But the default is that they interact at every time step. And when I say a time step, this is a time marching simulation, so that everything happens in the time domain, and there's very, very small time steps that occur between one step and the next to make sure that all dynamic loads are captured as they propagate from one element to the next. So we're typically talking of time steps of the order of milliseconds or fractions of a millisecond. So one of the other key aspects of this project is to incorporate these metal model laws that have failure in them, so that if a crack is going to develop, we can actually monitor that happening as the boat goes over the wave. So if this crack is in such a way that it's resulted in way beyond the yield of the material, then this crack will propagate in time as the boat goes over the waves. Or if it doesn't, we'll get a very accurate picture of the stresses around that so that we can use that for a fatigue assessment. So that's the model that we received from our partners of the boat. It's purely structural. There's no appendages, and it represents the boat in the as-built condition, if you like. But that's not really what we want. We really want to model a boat that's been in service for a while and has some sort of degradation. So we've had access to a large number of reports from the surveys of the boats that identify the kind of degradation that can occur. And the plan is, the aim is to model this sort of degradation in our models such that we can actually see the increase in stress associated with this, either a loss of material in the case of corrosion or these actual cracks in a structure. The other novel thing we're doing here is we're modeling not a complete wave or a complete wave tank, but only a section of the ocean and not down to the floor. Instead, we're looking at this as a subdomain concept, and people who do analysis will often look at subdomains. The subdomain of an aeroplane might be just the wing or might be just the tail. They know all the other loads that are acting around. So they don't need to model everything else because they're not interested in that. They're just interested in the detail area. So that's what we've done in our approach to modeling the waves. We know from airy waves theory that these wave particles, if you like. The water particles have this orbit, and the orbit decreases in diameter as you go down in depth. So basically at some depth, we know exactly what the orbit diameter is going to be. So if we define a limit to our tank there, we can define a flexible tank, and we can give that flexible tank the motions of what the water would have at that depth. And if we just move the floor, it's fascinating, but these waves develop on the surface that are much larger in amplitude than what you wiggle the floor at. And that's when my Chilean friends have come in, and they've understand the physics behind all this, and have written some papers which are about to be published on why this works. So the advantage of this is that you don't need to model the full length of the wave tank. You don't need to model the full depth of the wave tank or the ocean, whatever it is you're modeling. So you only have a much smaller area of fluid to model, and that's important to the CPU time for these large simulations. So here's just a demonstration that this technique works to produce this, or reproduce this orbital motion of the waves through the depth. So on the top left there's a long tank. We're wriggling the bottom, and then I've zoomed into this section in the middle where I've got some slightly finer particles, and we're still wriggling the bottom. That's what these little circular traces, these are the what we call the trajectory of a node in time. And then even throughout the depth of the water, we can take particular particles and we can trace their trajectory with time throughout the simulation. And at the floor, they're very small orbits. As you get up to the surface, the orbits get larger. And what's really fascinating is you even get a little bit of this downstream drift as the waves progress. So back to the ship, we need to demonstrate a few things like that it actually floats in the right place. And our first benchmark was the still water bending moment of our fully structural model floating in this SPH. So we've got a tank, we've got the model, we define water, define gravity, just like that first simple red cross-section of a boat that I had, but now we've got a slightly more complex model. I mentioned these contact interfaces. These are a rule in the industrial software that just keep particles from smashing through each other. So wherever there's a sliding interface or something like that, we can define this contact interface, and that prevents one material going through the other. But there's forces generated, as you would expect, when two materials or parts interact. So you can define the friction against these things, and the stickiness, if there's some stickiness, if they don't want to pull apart after they've been in contact. So that's what keeps the SPH particles outside of the boat and inside the tank, those contact interfaces. So here's the boat settled on its waterline, and well, it's not a very exciting animation, so I won't show you that one. But what's important is the hydrostatics. The boat appears to be sitting at about the right location. It's interesting, it wasn't until I did this simulation that I noticed the boat sat with a slight list. I went back and looked at the numbers, and its center of gravity is not exactly on the center line of the boat. Oh well, that's what it is. There's some internal structures in this boat that are not purely symmetric, so that's, I guess you can expect that. So as far as extracting loads and forces out of the boat model, the FEA model, we define these 10 sections where we're going to get really detailed results out of the boat. And particularly at these sections, we're going to get these complete shear forces and moments which act across this whole section. Otherwise, all we get is the local behavior of individual elements. If we want a complete section, we need to define all the elements and nodes and beams within that plane, if you like, where a frame might be, and then we can get a complete moment and shear force out on a particular section. So for the still water bending moment, this was the results that we got. There's still a slight error there, but you know, I think considering the totally different approaches to arriving at this result, this is a pretty good result. So I was pretty pleased with that. Again, another indication that at least the results are in right ballpark. Okay, some simulation results. This is where the software really comes into its own. You can actually visualize what's going on. So we've got moving floor for the waves. In this particular case, we use periodic boundary conditions. That means that for the water, that means that when the waves get to this point up here at the upstream end, or actually, sorry, the waves are actually propagating downwards. So when the waves get down to this point here, there's what we call a periodic boundary condition. That means that whatever happens here at this downstream end is replicated numerically up here at the upstream end. So basically these waves will propagate forever, and not decay, because as soon as they get down here, they re-interrupt the top. Obviously, we can't do that with a ship. So the ship starts down at one end, develop the waves, and get it to drive up into the waves. So the model ship can be either rigid or it can be a fully flexible ship. Obviously, if we want the stresses and strains from within the ship, it needs to be flexible. So there's a lot of different parameters that go into setting up these models. The size of the SPH, it's a bit like you know, the resolution, the size of the mesh in a CFD or even a conventional FEA. The tank parameters, the width, the depth, parameters, sorry. And then we're going to fix some things here like the wavelength, the speed, and the wave height. And then we're going to be looking to get the pitch and heave out to compare to the RAOs for this boat. So we did a sensitivity study. We looked at a bunch of these variables and then normalized the results. So this is some of the runs that we did and what we're going to vary. So in the first couple, you can see they're all large particle diameters, 1.2 meter diameter particle that weighs about 1.6 tons. So they're kind of heavy, these particles. It's not really smooth. It's a bit like sailing through icebergs, ice blocks. Anyways, it's a table of results that we varied to study how these parameters influence the response of the boat. One of the first ones was the depth. Now, because we have a moving floor that has to interact with the water to create waves on the surface, so there's a limit there. We can't go deeper than half a wavelength, because at half a wavelength, the diameter of those orbits is effectively 0. So we need to be in the order of, well, less than 50%, and 30 to 40 works quite well, but still gives you a reasonably deep tank. We found that slightly better results in each of these cases. The simulation kind of under-predicted the actual pitch and heave. So similarly, the domain width, there was something happening here at about 70 meters wide for this particular condition, but otherwise wider should have been better. This actually happened to coincide with the reflection off the side of the wall, perfectly meeting up with the transom of the boat. And then the other one, which is really important, was the SPH particle diameter. Basically, the smaller you go in SPH particles, the more it becomes like a continuum, if you like, and you get better results. But smaller particles also means there's a lot more particles, means more CPU effort. So there's got to be a compromise there, like all computational work. Oh, sorry, went too fast. This is the other drawback of large particles. This is the force acting on one of these frames that we were looking at. And because 0.9 meter particles, it's a relatively smooth force, still some noise on it, but using 1.8 meter particles, that same inherent signal is there, but there's so much more noise over it. So each of these particles is kind of like an immovable object that you've got to move, and you're having the ship bounces off these particles. So if you can have smaller particles, you get smaller impact forces with each particle. Okay, life's a compromise, and these are the parameters that we chose for a lot of our initial investigations. So that was really just to justify the parameters that we're using. But now this is interesting. So here's some real results of the boat as it goes over waves, and this is the moments created at the bending moment at each of those 10 sections as the boat goes over some waves. So you can see that they vary in magnitude of this purple line here. It has a magnitude of that, and its mean is about there, -30, whereas the green one probably closer towards the middle of the boat, much greater amplitude, and its mean is down around 50 or so. So this was some of the first real dynamic results that we could kind of have a look at and think, wow, that's fascinating. I hadn't really thought about that before, but it all seems to make sense. The other interesting thing is that there's a slight delay in time where the crest of most of these results occur. And I suppose that you can imagine that the crest of the boat, the crest of the wave takes a bit of time to go past each of these sections. So you don't expect the maximum to occur at the same time everywhere in the boat. And then we've since improved a lot on this, but the comparison of the bending moment with forward speed at one particular section compared to the Maestro. So we're a little bit under-predicted. I'm not too worried by that, and in fact we found some mistakes there, and our correlation is a little bit better since then. So this was also great and encouraging result, I feel, because again, we're taking a very different approach to the traditional naval architecture rules and methodology. We just got an FE model of a boat and we've got a wave, and we just let them interact, and this is the response of the structure. I think that's an important result. So the other nice thing about this is it's a finite element package, so we can look at stresses that occur in the boat with time as the boat goes over the waves. So here's just a snapshot of some of the stresses inside side plates of the boat, and we can see that where there's a drastic change in section between the aft flight deck there and the main superstructure, these yellow regions are typical of high stress, and they're kind of occurring exactly where you'd expect them to. So without any sort of real serious engineering validation, your engineering intuition should tell you that that's kind of what you'd expect. So again, that's kind of nice to see these sort of results in the FE when you first look at the results and you think, okay, yeah, that's good. So the work within the project now is trying to kind of validate a lot more of these stresses as the boat goes over waves and known conditions. But one thing that these simulations can do that other software can't necessarily is give you that movie of the boat as it goes through the waves. And I think that's a really important value of these sort of results is the animation. So if you can actually look at the boat, you can look at the motion of the ship, and if you've got any sort of feel for what the boat should be doing, you get a feel for whether or not the results are correct, or feeling that wow, that's not what I would have expected, and then you might go back and have a think why. So I'm just going to present here a couple of different results from our animations to illustrate what you can see. So here we are, 9 knots. The wavelength's about the same length of the boat, and we've got a 1 meter sea. Pretty benign. Not really very much happening. You can hardly say that's exciting in any way. But I still find it's very encouraging to see these sort of results. You can see here at the bows, a little bit of splash. Remember, we've got 1.2 meter particles, a ton of water in each of these. You're not going to see much splash. What is interesting is what happens at the transom here. You can see some water gets dragged along with the boat. And I think that's kind of novel. I'm not too sure how many other software packages will pick that up. And the motion, yeah, you can see a bit of pitch and a bit of heave going on there. So it all looks about right. So then we go to a 2 meter sea. The contour, by the way, the color of the particles just represents wave height. So you can visualize the waves as they come down. So now the foot of the bow is almost coming out of the water, and there's a bit more turbulence at the back end of the boat there. So some more water is getting dragged along with the boat. I think that's really interesting. In fact, you might almost think there's maybe even a hint of a rooster tail when the transom gets pushed down into the wave. And these are quite complex flow phenomena that we're not doing anything to model. They're just a result of the interaction of the boat with the water. And then as we progress to even bigger waves, we now have a 4 meter wave. Same boat speed, same wavelength. Now we're getting the foot of the bow is well and truly out of the water, so we might expect to see some slam there. And the flare of the bow is also being introduced. So there's some water being pushed sideways. And again, that interaction of the fluids at the transom is really quite pronounced now. There's really some movement going on there. It's kind of following the ship. It's kind of forming a rooster tail and then breaks open. So these sort of visualizations can greatly enhance your understanding of what the boat is experiencing. And when we start to look at the drag on the boat and things like this, there's reasons for why it fluctuates with time. So this same simulation, if we now change the contour of the SPH to be velocity, so now we're looking at the speed of the particles. So you can see that splash when the bow flare kind of hits the wave. There's a lot of water being pushed sideways. And again, that motion at the transom, the water on the surface of the transom is doing some very strange things. Yeah, so again, the visualization, you can learn a lot from that. Okay, now here's something which is totally outrageous. What the heck is going on here? All right, so this was a really interesting conversation and series of simulations. So radio, let's go and simulate that. So I simulate that, and we get this thing which is behaving like a rib with an outrageous outboard on the back, things leaping out of the waves. Okay, so obviously that's wrong. that's not right. Well, is it? I don't know. Has anyone driven a frigate of this size at 27 knots into an 11-metre sea? I imagine that would be exactly what would happen if you could do it. Thankfully, usually the captain has better sense than that, and he'll kind of throttle back a bit and just maintain steerage way. But there's a lot to be learned from here. Again, the simulation proceeded, even though we specified something that's probably unrealistic for the boat. The boat, for this particular case, the FE model was a rigid body, so we're not getting any stresses out of it. But the software didn't crash. It didn't say, hey, my boat's out of the water, I can't do this, or my bows are almost underwater, what's going on? It just soldiered on. So I think that demonstrates that you can specify quite severe conditions that you'd never expect to drive your boat through, analyze them, and get some sort of response. So yeah, it was an interesting result, even though we kind of disregarded it at the time and think it's totally wrong. And then going back to looking at the stresses in the boat. So here was a much earlier simulation where the boat has 0 forward velocity and just a wave going past. But what we're looking at is how the stresses develop throughout the ship with time. So obviously the red is high stress and blue is low stress. And you can see generally that those sort of things, where there's a period of high stress that associates with when the boat is going over the crest of the wave. And then also the foot of the wave, the foot of the bow, it's really quite interesting what's happening there. Keep in mind the bow of this boat is about 15 metres out of the water. And the bow's already, the foot of the bow is probably 2 or 3 metres below that. So what's happening here is we're seeing some large hydrostatic pressure on the foot of the bow as it goes down into, you know, what looks to be almost 20 metres deep. So that's, you know, that's kind of, you can understand it. It's obviously not a bending load, but when you understand the hydrostatic forces involved, that's what's going on at that point of the boat. So these animations are incredibly enlightening. Basically, that's where we were 8 months ago when we had to present this paper to the DST guys to get approval for publication. But it gives you a bit of a teaser as to what results are possible to come out of this sort of approach to the analysis of a boat and waves. So, as I mentioned, we're progressing still with this project, and we've progressed a lot further than what I can show you now, and we're getting some really interesting results showing the stress in greater detail under different conditions. But it's a really exciting project. So, as I mentioned, this paper was presented at Pacific 2019. Noise in the background is a dog trying to come in, wants to be a part of the presentation too. If you're interested in the paper, I didn't present, went at Pacific 2019, I'm happy to share that paper with you. And this boat doesn't experience much bending, but it was a boat that I saw when I was sailing in Indonesia last year. And look, you know, I feel for you guys in Melbourne. I hope you're all doing okay. There's a lot of similarities there. Be safe. Thank you for listening to my presentation.
All right, so one here from Phil. Do you want to, so was the same presentation as presented to New South Wales in March?
Yes, pretty much.
Okay.
Although back in March, we didn't know whether we had another 3 years of funding, so.
Oh, I'm hoping there's a few more out there. Robert, Rob Hayes, do you want to go along with yours? How long would a typical run take to compute?
Oh, that's a great question. How deep are your pockets? How long is a piece of string? How big is your computer? So a lot of these simulations have been done in the offices of Pacific ESI in Sydney. The rigid boat simulations run a lot quicker than the totally flexible finite element model simulations, and the rigid body runs typically run in about 12 to 18 hours on about 24 cores. But now that we're looking at the flexible ship and we're refining the mesh in areas where we have or hope to model cracks and corrosion, the simulations probably now run out to about 24 hours on probably about 50 or 70 cores. So we're at the moment, we're trying to kind of keep the model size to be no more than 1 or 2 days with the number of CPUs that we have available. We hope to be gaining access to some supercomputer time, and this will allow much greater resolution in both the finite element model of the boat, so that we can actually get down to much smaller elements. At the moment, in Pacific ESI, our mesh size is still much too large to model a crack, but it's giving us really good resolution of stress distributions in areas where we are interested in what the stresses are. But ultimately, the aim of the project was to look at cracks, and well, we've learned that we just need a lot more CPU grunt than what we have access to. So hopefully the access to the supercomputer will really present some really exciting results there.
Perfect. Thank you very much.
And from Jason McConaughey, performance of steep waves, do you achieve expected vertical and horizontal asymmetry for nonlinear waves?
Yes, that's quite a good question about the way the waves are developed. But yes, we do get quite increased steepness as the waves get larger. They do adopt the theoretical trochoidal form, and they will actually break if we make them too large. So this all appears to be following the physics quite well. And yeah, we get increased steepness with wave height to the point that the waves will actually break.
Okay. Andrew Baglan, how many particles are in your model? I think that's sort of part and parcel with the previous question.
Yeah, it is very much, but it's a good question. So there's the models like the one in the top left-hand corner of the title page. They would be used for the rigid body analysis, and we probably run about 600,000 particles in those. But as I mentioned, with the use of the supercomputer, our numbers with the speed increase and the time that we've got available, we're expecting to run certainly in the tens of millions of SPH particles.
Ben, Mr. Healy, do you want to present your one? I can't relate to that one, sorry.
Yeah, so I guess excellent presentation, Bruce, thank you. Question is about validation or V&V, and how do you approach V&V or making sure that your results are going to be appropriate? Is that done on a case-by-case basis, or do you think the results are typically accurate?
Look, that's an excellent question. If I can answer that first one. Yeah, that's an excellent question, and has been a large component of the work to date, is to convince the naval architect guys involved that our motions are reasonable, if not accurate. And I'll confess that initially some of those graphs indicated that we're kind of under-predicting the pitch and heave response of the boat into head seas. So we do know that moving just finer particles will improve that result. So again, having access to a supercomputer should enable much better results there. But there's an interesting kind of catch-22 here, and that is that you don't want to go and redefine the RAO for every boat that you're going to analyse. So what we're hoping is that once we've done a good validation for one particular boat or ship, and under those conditions, as long as we don't change our parameters in our model too much, I would be having an extreme amount of confidence that if we change the hull shape, that the predicted response is going to be very accurate. And then the other side of that, the flip side of that, is that I stated in the outset from this project that we're really interested in looking at kind of limit state conditions. And to be quite honest, finding the validation data for a boat that's about to break in half is a bit difficult. I shouldn't say break in half, that's not what we want to do, but those 27 knots at 11 metre seas, I don't know if anybody's got data for a boat doing that, but it's just difficult. I'm sensing from the partners that it's difficult to find that sort of data for validation outside of the linear range of the boat, out of the linear range of the response. But that's really where this tool is going. I really see this as a tool to be used where the conventional tools don't work. You know, you saw what can happen there. We can drive this thing at unrealistic velocities, and the simulation keeps on going. So that's where I think the value of this sort of tool is in those extreme wave, nonlinear events.
Excellent, thanks. And then comparison against Maestro. I mean, to me that indicates that, I don't know, I would have thought that a comparison would have been made against physical data as opposed to Maestro.
I'm just the bunny doing the work here, and it's up to our partners to provide data for that purposes. And so far, you know, I think the Maestro has been a good basis.
Right.
You saw some of the curves there, or maybe we're a little bit down on the bending moments, but some of the other results that we have been able to compare was some stresses in the top plates and stuff like that, and in the bottom plates, and we're getting very good correlation with. I'm not too sure if those results came out of Maestro, but I thought they were, and you know they were well within the 10 or 15%, which I would have thought for such a different approach to solving the problem is a pretty good result.
Yeah. Fair call. And the last question is, what are the typical setup times? So just say, you know, I gave you an oil and gas vessel, an anchor handler, and said, you know, I don't know, I guess it's how long is a piece of string, but you know, how complicated is it to set up a problem?
Look, what we found is that typical with any of these sort of high-end engineering solutions is the most difficult part is making sure that the data is in the right format. So for our particular case, the model that we received wasn't compatible with our software. There's a lot of tools and a lot of functionality to import FE models from other pieces of software, but there was still some conversion required. So that chewed up more time than actually the time taken to actually build the model and define the loads on it and set up a sea state and define a tank. So I guess, you know, if we were working with a customer regularly, we'd have that sort of process refined, and we could probably do it in a day or something like that. But to be quite honest, the first instance, it probably took us over a week to kind of get the Maestro model, FE model, into a format that we could use in our VPS software.
Yeah, okay, excellent. Thanks, Chris.
If it was just on that, if it was a rigid model and you were only looking at the loads on the boat, the pressure distributions, if you like, and you're only really interested in the motions, then it's a doddle, because it's really a piece of CAD can do it, an IGES file without any material data or anything like that, and without any structural details. We just need the outside of the boat, make sure the water stays on the outside, and you know that's something I could do before lunch.
Yeah, well, yeah,
if I wanted
to. Thanks.
All right, from Rob Hayes, again, can you analyse elements on the ship, such as the stern door, for example?
Do you want me to elaborate a little bit more on that? So that's basically where you've got moving elements. And so, for example, the LHD ships have got a stern door, which is subject to forces. And obviously, it's very much a non-linear, potentially a non-linear thing where the stern door can move basically relative to the ship, but also the ship's subject to movements. So it's getting an idea of that movement, which will then translate into forces on the hydraulic system or the structure, for example.
Yep. So look, to me, that just sounds like a conventional, explicit FE problem. So we have the ability in the VPS software to model springs and damper linkages. So we can define pivots. So we could have one piece which is totally rigid, or it could even be the representative structure, and we can get stresses in that door. And it could pivot or hinge around a known point, and then what holds it in place would be some sort of tension member or whatever, and we can measure the loads in that without a problem. This was a common problem for the bird strike with the control flaps. Because when the bird hit the flap, the transfer of that load into the rest of the structure was very critical, because obviously you didn't want it to, an essential part to break. So to me, it looks like exactly the same sort of problem. I don't see that as being a challenge at all.
Yeah. Thanks.
All right, Martin Grimm, you've got a couple there. Do you want to present the questions there?
Yeah, sure. Thanks, Jess, for the invite, and thank you, Bruce, for an excellent presentation. So I've got a bunch of questions. Years ago, the SPH calculations that you had, the waves damped out over time. It was with the waves into a well dock. I noticed you do the modelling of the domain quite differently than I think you did back then, but I had a sense that maybe there was sort of like a numerical damping going on. What's the status with that in the meantime? And then two other questions.
Look, for that first question, thanks for reminding me of those problems that we had back then. But yes, the SPH is inherently lossy, but the first time I presented any of this sort of stuff was probably 2006, 2007, 8, whatever. And yes, the whole reason to develop this moving floor technique was partly to overcome that damping, and that we couldn't actually get waves to maintain any sort of a useful amplitude if we just started at one end and have them propagate down a tank like you would in a wave tank. So the moving floor overcame that because we only had the depth through which to lose energy compared to along the whole length of the tank. So that was then, but what's really been amazing is my colleagues in Europe, who are the authors of the software, they continuously rake the scientific literature, and we've got a lot of current technology I shouldn't say technology, but the current algorithms adopted into our software, and even little things like there's particle motion correction and there's pressure corrections and all these sort of things. And what we're finding is that we're orders of magnitude better in the loss area than we used to be. So although I'm still developing my waves by moving the floor, what we find is when we stop moving the floor, the waves will still propagate for a lot longer than they used to. I think that they probably still do damp down excessively compared to water, but the losses are nowhere near what we originally had. So I'd like to think that the situation of the LH2 wet dock there, I think that we'd probably get some useful wave propagation within that still.
All right, perfect.
Those sort of dimensions, yeah.
Yeah, thank you. Look, my second question was more a comment. I'm just wondering whether the Maestro, I think you sort of take the Maestro as being somewhat of a definitive statement. I mean, that's the way it came across in your presentation. I wouldn't necessarily. You may well have better results than Maestro. There's plenty of other codes, at least ShipMo 7 used to do internal structural loads and seemed to do it quite well. So, you know, you can look at other codes for validation, and there are model test results out for certain models that people have tested over the years. So, you know, that's something that DST and you could talk about. But look, my final one is just a private interest. Flow of SPH over foils or wings. Is that something you've ever tried to tinker with, and would it actually calculate the lift on a foil?
I'll say yes. I'm aware of, look, many years ago I did a very simple foil demonstration, and we can generate the lift and drag off a foil. I haven't been back there to look at that, but I don't see why not. I know my colleague in Holland with the software a couple of years ago was looking at the well, not necessarily cavitation, but certainly ways to model the loss of adherence of the flow on the backside. So look, I know there's some been work done in that area, but that's not an area I've followed closely. I agree. It would be interesting to kind of get into.
Fair enough.
There's so many interesting things out there. Not enough time.
Sure. Okay. Thank you.
Thanks for your questions.
All right. So I can see there's a couple peeling away from the meeting, but I think we'll go on a little bit longer. This is some good value out of the question session. So we've got a few more to go there, Bruce. So hopefully you're okay to take a few more.
Sure.
I'll go over to Kim. You got a question there? Yeah. Kim Clacker?
Hang on a minute, I'll just get the video going so you can see who's talking. Yeah. Bruce, thanks very much for a great presentation. Very, very clear indeed. And massive progress since I last heard from you, must be a decade ago.
Yes,
to
would be.
start baby steps of validation, have you got validation of, say, pitch and heave RAOs against either tank test data or strip theory or some other established method?
I thought Maestro would have conformed to one of those.
Yeah, well, Maestro, you've done bending moments against Maestro, but I just haven't seen a pitch and heave RAOs.
Oh, sorry, I didn't include them, but no, we have been using those. Yeah, that's as I mentioned, we to date we kind of underpredict what the Maestro response in pitch and heave is predicting for this boat. So maybe we've got some work to do there. Maybe we just need to ensure that our models are exactly the same or something else. But yeah. As far as correlation to a model experiment or anything like that, we haven't. I've been using the data provided to me, and that's been the Maestro data.
Yeah, thanks. Yeah, it certainly all looks very realistic. It's just it'd be lovely to have the numbers to prove it.
We're working on that.
Thanks.
Mm-hmm. Thanks, Kim. So Kerry Johnson, hopefully I can do this justice. So how's flow rate through openings handled with respect to the relative size of the opening and particle sizes?
Yeah, that's a good question. And there is an application that I have studied a little bit at. I've looked at some of the flow through an orifice, particularly a submerged orifice between two tanks as a calibration. And yes, particle size is very important. So as long as your orifice diameter is, 50 or 100 times bigger than your particles, then you're probably going to be doing all right. But the other thing I did notice was that edge sharpness was a big thing. So, the kind of feature size relative to the particle becomes important then. So it's, yeah, I guess it depends what your real interest is in the solution. Is it the bulk flow, or is it detail around edges of these orifices and stuff like that? And I guess it is pretty CPU intensive, so you need to choose the parameters and the size of your model to reveal the data that you want, or the results that you want. So all I can say is, yes, around sharp openings like an orifice, it is quite sensitive to the particle size.
Thank you. All right, so we've got 3 more questions, and I might close it off at XU's question. There's the last one. So from Shannon Phillips. Shannon, you might be best presented. I see ale there, and I think beer, but I'm pretty sure it's not that. So I want to present your question.
Yeah, so ALE's arbitrary Lagrangian Eulerian mesh. I was just wondering if there's an advantage to using SPH over AL, if you've had any experience with that, Bruce.
Look, I haven't, and I'm not even going to attempt to answer that question because I just don't know anything about ALE.
Okay,
so
no worries.
One of my other colleagues could, so if you want to drop us a line, or I don't know. But no, that's not my specialty, so I'm not going to go there.
Fair enough. Thanks for your
help. From Andrew Baglin, have you looked at more complex wave states, such as a John Swap spectrum type waves?
Look, that's certainly on the cards, and that's certainly our aim in the next phase of the project. But our aim to date has really just been to satisfy ourselves that the response is appropriate, and for that, just a single frequency seems to work right. We've thought about it. It's not going to be easy through a moving floor, but it should be possible. I've certainly demonstrated more than one frequency at a time in the waves. So it's a matter of what sort of resolution we really need to accurately define the motion of the boat that we want. Again, it comes back, as far as I see it, as to what you're really trying to do. If you're after a specific impact event, then I think it'd be far better to have some sort of design wave train where you know exactly when the waves are going to come and hit your boat. And it's the way I tend to be leaning as far as if I have any influence over the way the project goes in the next phase. So rather than run some statistical wave group and just wait and run it for long enough that you get your impact event, I much prefer the idea of a design wave train, if you like, such that you can run exactly that same wave train and get that same impact at a known time, at a known location in the tank. And then that presents a much more reliable way to do a what-if analysis. If you want to vary the structure between the boat, you know, okay, this sort of reinforcement or whatever, the stress has only got to this. What if we did this, or what if we did something else? I just see a design wave as being a much more useful tool for a repeatable situation.
All right, thanks. Thanks, Andrew. Thanks, Bruce. Just final one then from XU. The modelling shows stress concentrations around sharp corners. To what level are the stress concentrations caused by the structural design? And what are the possibilities of using modelling results to inform design improvements around structures, I presume?
Well, yeah, that's a good question. Thank you. I wonder if that's Xiaobo out there. Hi, Xiaobo. Obviously, the whole crux of this is to be able to predict the stresses in areas of stress concentration. Whether or not we'd be influencing at the design outset, that wasn't really the aim for the tool, but we're more looking at existing structures and stress raises that have resulted in a consequence from, or as a consequence from use. So either fatigue cracks or damage, if there was an accident or an explosion or something like that, or loss of material due to corrosion. So that would be a little bit different to the approach that, and probably the results that you want from a design outset. But ultimately, the principle is the same. So yes, if we can identify before a vessel is built that there's going to be a problem in a particular area, then yeah, of course we could use that for this, or this for that particular application. And maybe a very interesting one there would be a better accuracy on predicted fatigue life. If we can more accurately define the stresses, if we actually know what the sea state of boat is going to spend the majority of its time in, for example, we might approach the fatigue life in a different way of a new boat. I don't know that we're going to have the confidence of the builders or the designers yet to change their decisions or their design, but it might be useful to have that information at our fingertips.